Okay, we're going to apply a Runge-Kutta method to the second order differential equation. Now, before we do that, we need to convert the second order equation into a system of first order equations. Runge-Kutta methods can be applied to first order equations. I'll just put first order ODEs. So we need to convert the second order equation into first orders. Now, the way we do that is we define some new variables. So let's define, we're going to define u1 to be y and u2 to be y prime. And we're going to stop there because the number of variables that we need to define, in this case, u1, u2, we have two variables that we need to define. That should match the number of derivatives in your ODE, so the order of your differential equation. The highest order of the derivative that appears is the number of new variables you'll need. Now we're going to write down a system of differential equations in u1 and u2. So we shouldn't have any y's appearing in our new system. To do that, we are going to take the derivatives, so u1 prime and u2 prime. u1 prime is really y prime because u1 is y. So this is y prime. But I want to write this system in terms of u's only. So I'm going to look back up here and see that y prime is equal to u2. So u1 prime in terms of the u's is equal to u2. Now u2 prime, well, let's see, u2 was y prime. So if I take another derivative, this is y double prime. I don't have a u for y double prime, but I do have an expression up here that involves y double prime. And if I go back up here and I solve for y double prime in terms of y and y prime, I have that y double prime is negative 10y minus 2y prime. And then remember that y is u1 and y prime is u2. So this is y double prime, which I said was negative 10y minus 2y prime. But I want my system to be only involving u's. So I'll replace y by u1, and I'll replace y prime by u2. Now I also need to transform my initial conditions in terms of u1 and u2. u1 at 0, well, u1 is y, so u1 at 0 is y at 0. And in this case, that's 2. And u2 at 0, u2 is y prime, so this is y prime at t equals 0. So this is 0 from this initial condition. So this is my new system. And if you wanted to write it a little more cleanly, so I'll sort of write it all without the y's involved at all. So I'll do this like in a different color. Okay, so I have u1 prime is equal to u2. u2 prime is negative 10u1 minus 2u2. u1 at 0 is 2, and u2 at 0 is 0. This is the system I then want to apply my Runge-Kutta methods to. And I'm going to switch over to MATLAB and show you how we would do that. Okay, now that we're over here in MATLAB, let me walk you through how you might solve the problem that we just outlined on the in our notes. So in your project, you are going to implement Runge-Kutta order 4. So there's going to be like 4 intermediate steps that you need to perform before you update your solution approximation. The W's here represent approximations to the solution, y. And so wi plus 1 is the y evaluated at time, ti plus 1. W sub 0 is the initial condition, and you'll implement this in your project. But to give you a sense of how that might go, I'm going to help you implement a different Runge-Kutta method in this video, and then I want you to adapt what you learn here into your project. So in this video, we're going to implement Runge-Kutta order 2. This is not the one you'll do in your project, but it should give you an idea of how it'll go. So let's say we have a first order initial value problem. And this Runge-Kutta method says that we start with our initial condition, and in order to get to the next step in our approximation, we take the previous step plus 1/4 times k1 plus 3k2, where k1 is h times, I'll do this, oops, sorry about that. K1 is h times f, where f is the right-hand side function, evaluated at ti and wi, so the previous steps. And k2 is h times, again, f evaluated at a certain place, but this time it's ti plus 2/3 h. And then you also evaluate at wi plus 2/3 k1, where we've defined k1 up here. So this is the method we're going to implement, and we are going to do so on the example problem that we had earlier. So we're going to apply Runge-Kutta method order 2 to this second order initial value problem. We're going to do this over the interval from 0 to 5, and so 0 to 5, and with 500 integration steps, let's say. Now, we already saw in the previous notes how we would write this second order equation and its initial conditions as a system of first order equations. That's what I have listed here. So if you need more help figuring out how we got to this stage, I would say go back in the video and sort of rewatch that portion. Now I'm going to move on to programming this down here. So I am going to pull up a second copy of this problem so that I can reference it on the same screen. Move this over. Okay, so here's the problem we're trying to implement. And I'm going to go down here and start programming this. Okay, so we want our time interval to be from 0 to 5. So I have first set up that my left endpoint is 0 and my right endpoint is 5. I want to take 500 integration steps, so I've defined this variable n to be 500. And I'm going to need a step size when I perform this integration. So if you go back up here and look at the method, h shows up in a lot of places. That is our step size. Okay? And the step size is b minus a over capital N. So that's what I've defined here. Now the vector, we can actually define the vector t. This is our mesh points, or our vector of time values. And we can define this as starting at our left endpoint, ending at our right endpoint, and taking steps of size h. You could have also used the linspace command. The syntax is starting value, ending value, and then number of mesh points. The number of mesh points will be n plus 1 because we're including the first point here. So this is like the first point, and then we take 500 steps. So it's 1 plus 500. Now next, I am initializing U1 and U2 here. So I'm saying, oops, I am defining a vector full of zeros for U1, and I want it to have the same size as the time vector. So that's how many integration steps I'm doing. And then I also define U2 in the same way. This just makes like a placeholder for MATLAB to then fill in all of the zeros with the actual approximations. Now to start out, I'm setting up my initial conditions. I want the first element of U1 to be the initial value of U1, which is 2, and the first element of U2 to be the initial value of U2, which is 0. This part's a little bit redundant because U2 already contains a bunch of zeros, so I didn't really need to do that, but just for completeness, in case you want to change the initial conditions, I'm sort of setting that up here. Okay. Now I'm going to do this next part sort of on the fly. I know it was already on the screen, but I'm going to sort of type it out with you. The Runge-Kutta methods require me to evaluate at my right-hand side functions. So I have a derivative equals some right-hand side. So if I go down and I look at the right-hand sides here, now I have two equations. I have a derivative for U1 and I have a derivative for U2. So I'm going to need to define two functions. I'm going to need to define one right-hand side function for u1 and another one for u2. So I'm going to call the first one f1, and it's going to be an anonymous function, and I want the inputs to be t, u1, and u2. And my right-hand side for u1 prime is just u2. I'm going to do the same thing, similar idea, for u1, u2. For f2, this is the right-hand side of the u2 prime function. That's negative 10 times u1 minus 2 times u2. So those are my two anonymous functions. I did include the t here, and in this case, it's not necessary because there's no t showing up on the right-hand side. But if there were, so if there are situations where there are functions of t on the right-hand side, so it's sort of good practice. Okay, you could have also done this in a vector format. I'm just showing it to you outside of a vector because I think it might be a little easier to digest what's happening. Okay, now we're going to start applying this Runge-Kutta method. I'm going to give myself a little bit of room here. If you look at the method itself, in this case, we're doing a second order method. In your project, you'll do a fourth order method. So you'll have 4 Ks to define. In this example, we're only going to define these 2. And I need to define each of these K values for U1 and for U2. So I'm going to end up with 4 in this case. So I'll have K1 for U1. I'll just say it like that, K1, U1. That's equal to H times F evaluated at Ti, Wi. Now my loop here is going from 1 to n because I am going to update U1 j plus 1 and U2 j plus 1 in the way that it's written over here. If you want, you could make this loop from 2 to n plus 1 and then update uj, u1j and u2j using j minus 1 indices on the right. I'm only doing it this way so that you can sort of see exactly where each of these pieces is coming from. Okay, so we want to evaluate f for the u1 case at tj in this case and wj. So f evaluated at the jth, because j is my loop interval, I'm not using I, I'm using j. So j, u1j, u2j. And I actually have an error here because I don't just want f. F doesn't exist in this code. I have f1. That's the function corresponding to u1. So that should be f1. So that's k1, u1. I also need k2 for u1. That's h times my function. I'm going to copy and paste this for a second. It's my function evaluated, but not just at tj. It's tj plus 2/3 h. So plus 2/3 times h. And then over here, I have wi plus 2/3 k1. I need to include that in both of these arguments. So u1j plus 2/3 times k1. And I need that same term here. So let me zoom out a little bit so you can see all of it. So ti plus 2/3 h, ti plus 2/3 h. And then I have wi plus 2/3 k1 in each of these components. So those are my k's for u1, and I'm going to need the same idea, but for the u2 variables. So I'm going to update all of the things I need to update here. The f should be f2 because I'm thinking about this equation with u prime. Sorry, let me scroll down a little bit. I need to apply it to this equation, so I need to use f2. Okay, oops. Let's go back up here. So I have f, and I have some errors up here. So this is not just k1 because k1 doesn't exist in my code. I have k1 u1. So let me make this k1 u1. This one is also k1 u1. Now down here, when I do u1 of j plus 2/3 k1, in this case u2, and this is k1 u2. Okay, so now I have my two differential equations. They look like they're in this form now. Now I need to update u2 and u1. So the next step, it's going to be the previous step. So at this point, I'm implementing this part of the code. U1, j plus 1, is U at j plus 1/4 times k1 plus 3 times k2, where the k1 and the k2 correspond to the U1 equation. So this is plus 1/4 times k1 u1 plus 3 times k2 u1. So this is k2, but it corresponds to the u1 equation. And then I'm going to have a very similar update. Oh, here this should be u1. This should be u2. And then I'm updating these k's should correspond to u2 in the second equation. And that should be it, really. If you had more equations or a higher order differential equation, you would have another line down here, and you'd have to define more k's for each of those equations. When you're doing your project, you'll be implementing a different Runge-Kutta method. You'll actually have 4 k values for each differential equation you're solving. So you'll implement that in this way. So I'm going to go down here, and then after this runs, I'm going to plot U1 and U2 in separate figures, and I'm going to talk about what those represent. So let's move this out of the way. These are my notes, and let's move this over here so you can see what's going to happen when I run this. I don't know why that's not. Oh well, that just seems like it's not going away. Okay, let's run this code. Yay, no errors. Okay. So let's go down here. If you're interested in making your plots look a little bit nicer, you can see that I've used a LaTeX in my plotting labels. I've also made the font larger using these 2 commands. Now this first plot is of y of t. When I plot u1 over time, that corresponds to y of t because that's how I defined u1 when I rewrote the equation as a system of first order equations instead of a higher order second order equation. So this is, if I plot u1, that's a plot of y. Now if I plot u2, remember u2 is y prime. So if I plot u2, I actually have a plot of the derivative of y. And for these types of problems, so for something like this type of initial value problem, this comes up a lot in physics as maybe like a harmonic oscillation, so like a pendulum swinging or a circuit, an electric circuit. And so you would be plotting, if this was a pendulum, y of t would be the position of the pendulum over time, and this plot of y prime would be the pendulum's velocity over time. So I hope you found this helpful, and I hope that it helps you with your project. Remember, in your project, you are going to implement a different Runge-Kutta method, but hopefully this video helps guide you along the way. Let me know if you have any questions. I'd be happy to help.